Hello everyone and welcome back to this tutorial. In the last tutorial we found a formula for the reflection coefficient, and in this tutorial we're going to study and realize that actually we can find the reflection coefficient along any point on the transmission line. It does not have to be at the end where x equals 0. It can be at any x. So for example, if you want to know what is the reflection coefficient at any position x here along the line, we can also do that. So how do we do that? So before doing that, let us define a formula, an equation for the actual voltage along this transmission line. So usually I like to write this equation as follows. So the voltage V on the transmission line will be equal to the voltage V plus, which is the voltage going in that direction. This is the amplitude, and also because it's a wave, remember that the voltage is a wave, we write the wave as an exponential, and this exponential will be equal to a constant that we call gamma, which is not this gamma, times x. So this is the wave going in this direction to the right here, along the direction where x decreases. Now let's think about this equation here. When x equals 0, which is this point here right at the load, the e to the x becomes e to the 0, which is just equal to 1. And so the result is just equal to V plus. So this V plus means or represents the voltage right at the load here. But it's not the total voltage at the load. It's just the value of the forward or the incidence wave, the wave that is traveling from the left to right. So when x equals 0, we have V plus, and when x increases, because x increasing is this direction here, the exponential here increases, so the total voltage increases, which makes sense because remember that at the generator the voltage is the highest, the amplitude is the highest here. So as x decreases, goes towards 0, the voltage should decrease. Okay, so now let us add the reflected voltage. Remember, we have a reflected voltage V minus that goes from right to left. So this is going to be V minus times the exponential of minus gamma times x. Now, in the same way as x equals 0, the exponential is equal to 1, and we are just left with V minus. We're going to talk about what V minus is in just a moment. And as x increases, this exponential here will decrease. So the amplitude will decrease as we go from right to left. So this makes sense, right? So we start with the voltage at the driver with the original amplitude. As it goes towards the right, the amplitude decreases. Then it hits the load here, it is reflected, and the voltage reflected, which is this component here, will also decrease in amplitude as it goes from right to left. Okay, so what is this gamma here? Okay, so the gamma, this gamma parameter here, is defined as the square root of z times y. So if you watch the first tutorial where I confused the z naught, where z naught is z over y, I confused it with gamma. So gamma is the square root of z times y. So remember that we can also write this as r plus j omega l times g plus j omega c. And remember that for a lossless line, r and g are equal to 0. So this will be, if r and g are equal to 0, then we just multiply these two. So j times j is minus 1, so you get minus. Then omega times omega is omega squared, and L times C goes here. So this will be equal to, now this square root, this minus sign here becomes a J, and this becomes omega times the square root of LC. So this is gamma. So we see here that if the line is lossless, if there are no resistances, then this parameter gamma here is purely imaginary. Now, we also write gamma because gamma can have an imaginary part and a real part. If the line is not lossless, then it will have a real part. What does having a real part mean? If you look at this exponential here, the exponential will be, first let me write gamma is equal to alpha plus j times beta. This is the same number as this. If gamma here is purely imaginary, then this exponential here is also imaginary, in the sense that if you raise e to the j beta, you get a cosine of beta plus j sine beta. So it will have, you can use the Euler formula, and then if alpha is non-zero here, then we have also an exponential here, which the exponential which causes a decay in the amplitude of the voltage. So the fact that gamma here is only imaginary means that this component here of the voltage will be purely imaginary, because we have to take the real part. In the end, we take the real part of the component here. So let's write. So right now, gamma is equal to j times omega times the square root of LC. So gamma is equal to alpha is equal to 0. So this is equal to j times beta only, where beta is equal to omega times the square root of L times C. Okay, so let's see here. Remember that we have V plus e to the gamma x, which is equal to V plus. Now gamma is equal to j times beta, so we have e raised to the j times beta and x. And so this is equal to V plus times, if you remember Euler's formula, this is equal to the cosine of beta x plus j times the sine of beta x. Okay, so this is equal to V plus, and now this is only a phasor representation of the voltage. So in the end, we have to take the real part of this component here. So the real part of this is just the cosine of beta times x. So this is the actual voltage if the line is lossless. If the line was not lossless, then this alpha would have a value, and so there would be an exponential here, e to the alpha times x as well, and this means that there is an e to the alpha x here as well. So this causes a decay in the signal amplitude along the line. So as you can see here, when x is equal to 0, this is equal to 1. When x equals 0, here the cosine is also equal to 1, and we have V plus. Okay, so this is what gamma is. This is the value of gamma. Okay, so now that I have demonstrated what this equation here looks like, we can go ahead and try to calculate the reflection coefficients along any point on the line here. Okay, so how do we do that? Remember that the reflection coefficient is the value of the reflected amplitude along this direction divided by the amplitude along that direction. So let's get some space here. Let me just copy this stuff here and put it at the bottom. Okay, so let's now calculate the reflection coefficient gamma x. Gamma x, which is equal to, so this is the point x, so this will be equal to V minus at x divided by V plus at x. Okay, so now we have to, so this is V, so now we have to find what is the value of V plus at the position x here. So let's write V plus at x is going to be equal to, now we use this value here on this position. So at this position X here, remember that we start with the voltage at this, remember that this is V plus here, V plus, which is the value of the wave going to the right at this point. So we need to find what is the value of this of the wave at this point X here. So remember that as we go from right to left, the value of this voltage increases. So this will be equal to V plus times E to the J beta times X at this point. Now, I'm not sure if it's, I think instead of writing J beta, I will assume that the line is not lossless, just for now. So this is V plus E to the gamma X. Remember that when X is equal to 0, we are left with V plus. And as X increases, this value increases and we get the amplitude here at X. So this is the V plus at X. Okay, so now we have to calculate what is the V minus at X. So V minus at X, V minus at X will be equal to, okay, so now we have to find what is the value of V minus at X here. So V minus, we start with V plus going this direction. When it hits here, it becomes V minus, because V minus is the reflected voltage after we multiply V plus by gamma. So actually V minus is V plus times gamma. So when this voltage hits this point, it becomes V minus, so we get V minus. And then what happens? As the voltage travels from right to left here, it will be multiplied by gamma, which means it will be decreased in amplitude and also shifted in phase, because gamma is a complex number. Remember, we are not assuming at the moment that the line is lossless. If the line was lossless, there will be no decrease in amplitude, just changing phase. But gamma here is a complex number. So as the line goes from right to left, we get the V minus is multiplied by minus gamma X, because this is as the line travels, as the voltage travels from right to left, X increases. So we have to multiply this X here by minus to make sure that our amplitude decreases. So this is what the V minus at X is. So remember that our coefficient is V minus divided by V plus at X. So all we have to do is divide these two terms here. So this is equal to V minus times e to the minus gamma X, which is the V minus at that point, divided by V plus times e to the gamma X, and this is equal to V minus divided by V plus times e. Now e to the minus gamma X divided by gamma X is just equal to minus 2 times gamma X. And now the last step is just to substitute. Remember that V minus divided by V plus is equal to gamma. So this is equal to gamma, which we also write as gamma naught sometimes, times e to the minus 2 gamma X. And that's how we calculate the reflection coefficients at any point on the line. So remember that we don't have only the reflection coefficients at the load here. If we substitute X equals 0, we just get excuse me, we just get gamma naught. So we can see that the formula is true. So as we go from right to left, the coefficient will change because the voltages will change here. So we can calculate the reflection coefficient at any point. We'll use this to calculate the impedance of the line at any point on the next video. So thank you very much for watching.